Hey guys, we're going to introduce some properties of logarithms, a little bit longer lesson, so I'm going to move through it pretty quickly. But just a reminder that we have an exponential and a logarithmic equation that we've just talked about, and we talked about how those are inverses. So if you recall, inverses on a graph are always reflected over the line y equals x. So here is our exponential equation, y equals b to the x. Here's the logarithmic equation. You can tell they are reflections over, if I can get that on there, sorry. You can tell that those graphs are a reflection over the line y equals x. The value of our b is going to help us define the specific shape of, or the steepness of our graph. So I did a more specific example. If b was equal to 2, here is y equals 2 to the x. There is log base 2 of x. Just the steepness changes a little bit, but still inverses. Okay, so we're going to introduce, knowing that they're inverses, we're going to introduce a couple properties that helps us simplify or rewrite things. So since logarithms and exponentials are inverses, if we have b to the power of log base b, these two parts cancel off. The b and the log base b cancel, and you're just left with that x. So anytime you see b to the log base same b, you're just going to be left with that x value. Likewise, in the reverse order, log base b of b to the x is just x also. That log base b and the b cancel one another off. For an example, if we have log base 5 of 5 to the 2c plus 3, that log base 5 and the 5 cancel one another off according to this rule. So we're strictly left with that exponent, which is 2c plus 3. Okay, use of the other rule to simplify 2 to the power of log base 2 of p. The 2 and the log base 2 cancel, leaving you with p. We talked last lesson about common logarithms being that logarithm base 10. Well, in order to use our calculator, it needs to be that common log, and not every logarithm we are going to work with will be a common logarithm. So we have this change of base formula to get us into a common log. So it's just what I said. Calculators are generally common log, which is base 10. So we have any logarithm with whatever base it is, we can rewrite that logarithm in this formula so that we can use our calculator. When we rewrite it here, notice that both the numerator and the denominator are now common logs. We don't write that base, so we assume that it is 10. So log base b of x can be rewritten as log of x divided by log of b, and that will give you an equivalent expression. So if we have log base 4 of 8, we can rewrite this so that we can actually get a numerical value. We can rewrite it as log of 8 over log of 4. Type both of these into your calculator, and you should get 1.5. Your calculators generally populate parentheses, so you would need to do log 8 end parenthesis over log 4 end parenthesis. Okay, we're going to look at rewriting this logarithm to help us introduce our next rule. So 32 is the product of 4 and 8. So we could rewrite this as log base 2 of 4 times 8. And if we rewrite these logarithms in exponential form like we did a couple days ago, log base 2 to the 4, or excuse me, log base 2 of 4 means 2 to what power gives me 4? Well, we know 2 squared gives us 4. Similarly, log base 2 of 8 is asking what exponent gives me 8 when my base is 2, and that would be 3. So log base 2 of 32 we can rewrite also as 2 to the x equals 32, and we would just know based off of our previous knowledge that x would have to be 5. Well, we can also get 5 by adding 2 plus 3. So our rule is going to tell us that we can break a product into its factors and add those two solutions together. So here's our product property of logarithms. If you have a log base b of some product, you can split that product up into an addition problem. So here's an example. We're going to approximate our log base 3 of 63. We're given that log base 3 of 7 is roughly that 1.77 number. Now, In order to solve the rest of this, we have to think what multiplies to 63, 7 and what? Well, we can rewrite that as log base 3 of 7 times 9. According to our previous rule, we can do log base 3 of 7 plus log base 3 of 9. We are given this decimal approximation right here. And log base 3 of 9 can be rewritten as 3 to what power gives me 9? Well, we know 3 squared is 9. So we have 1.7712 plus 2 gives us our answer of 3.7712. I want you guys to do this one. Okay, we just did product property and that split our product into an addition problem. Here we have quotient property of logs. We're going to take a quotient or a division problem and split it up using subtraction. For example, log base 4 of 6, we're going to evaluate that knowing that log base 4 of 48 is that, and log base 4 of 8 is 1.5. Obviously, 48 divided by 8 gives us 6, so we can take log base 4 of 6, rewrite 6 as 48 over 8, split this into a subtraction problem, so log base 4 of 48 minus log base 4 of 8, and then use our two decimal approximations to get 1.2925. Okay, so we've been talking about logarithms. There's one more type of logarithm. It's called a natural log. A natural log is always a base e, and it's written ln. So you have a button on your calculator that's ln, and that stands for natural log. Just a couple good facts to know. E to the 0 is equal to 1 because anything to the 0 power is 1. So we can rewrite that as natural log of 1 equals 0. Natural log does not need a base. Natural log is just assumed to have that base e. Here's another way we can take an exponential equation and rewrite it as a natural log. So e squared is roughly 7.39. Written in logarithmic form, it would be natural log of 7.39 equals 2. Again, we can simplify using our product and quotient rules this natural log. So natural log of e to the 4th divided by 3, knowing natural log of 3 as a decimal. We can rewrite this as natural log of e to the 4th minus natural log of 3. Since natural log and e are inverses of one another, we can use that inverse property that we defined for logarithms, and that simplifies to 4 minus that decimal gives us about 2.9014. One more rule. If we have a logarithm to a power, the power property tells us we can take that power and pull it out in front of our log. So log base b of a to the p power becomes p times log base b of a. For an example, if we have log base 3 of 81 squared, that 2 gets pulled out in front of our logarithm, so now it's 2 times log base 3 of 81. You can actually simplify this further. If you think about this logarithm as an exponential, you would rewrite it as 3 to the x equals 81. You can solve for x just thinking 3 to what power would give me 81? Well, that's 4. So technically this log base 3 of 81 is 4, and you can simplify this entire expression to 8. One last example, we're going to take this natural log and rewrite it as a sum or difference of natural logs. So first thing to do, kind of work your way backwards, is to pull that power out. So 2 times natural log of 5e over x. Now we have a quotient, so we're going to split it into a subtraction problem. But this exponent went to both the 5e and the x, so we have to write our remaining difference in parentheses. Then we can take this first piece, that is a product, 5 times e. We can split that into an addition problem. Still keep that 2 around everything. So that becomes natural log of 5 plus natural log of e minus natural log of x. And hopefully you remember natural log of e is just 1. They're inverses of one another. So we have 2 natural log of 5 plus 1 minus natural log of x. And then the last step would just be to distribute that 2 all the way through.